Hi, I'm Matt Balhoff, Associate Professor in Petroleum Engineering at the University of Texas at Austin. This is part 5 of our review of computer programming and linear systems of equations. This is the 5th part again, and it's going to cover linear systems of equations. Before we get started, I thought I would do one more example of just general programming and using loops and function files. So let's pretend, and as always, we program with a pencil and a paper. We don't need to use a computer until the very end. So what I want to do is I want to write a function file to multiply an n by m matrix by an m by 1 vector. So the matrix we'll call A, and the vector we'll call X to get an m by 1, an n by 1 vector B. Right? So what we want to do is we want to take a matrix A, and I'll say that these are A11, A12, A13, A1n, I guess that's M, A21, A22, A23, all the way to AN1, AN2 to ANM. So this has got n rows and m columns. And we want to multiply it by a vector, x1, x2, all the way to xm. To get our new vector b, b2, which will be n. So if this is an n by m matrix, and this is an m by 1 vector, the inner dimensions would degree, and we'd be left with an n by 1 vector. That's what we should get. Now, if it's been a while since you've done matrix vector multiplication, kind of the way we do that is we say that B1 is equal to the dot product of the first row in this column. So B1 would be A11 x1 plus A12 x2 plus dot 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 A1m xm. Right? That's how that would be. B2 would be A21 x1, A22 x2 plus A2m xm. And we go all the way to Bn, which is AN1 x1 all the way to ANM xm. That is how we would do this by hand, right? And if you want to make up an A matrix and an X vector and put in numbers and do it, and of course in Matlab you can just multiply A times X and it would give you the answer, but I'm not going to let you off that easy. I want you to do draw a loop and to kind of show you how it's, to give you some practice in doing some loops. So this is how we would do it by hand. You can put in numbers and do it by hand if you want to. You should have done matrix vector multiplication in high school at some point. So you can look up on the internet how you do matrix vector multiplication if this still doesn't make sense. But that's basically how you do it. You do B1 is equal to that, B2 is equal to that, Bn is equal to that. And we want to have a function file to do that. So step 1, let's write the first line of code for a function file, right? So we'll call it matvec.m. That'll be the name of our function file. What are our inputs? Well, our inputs are going to be the matrix A and the vector X. Our outputs are going to be the vector B. So function B is equal to matvec AX. That's the first line of your code. We're in good shape. Okay. Let's come back to here now. So what do I want to do? I want to calculate B1, then I want to calculate B2, then I want to calculate B3, then I want to calculate go all the way to Bn. So I want to calculate the n elements of B. Okay, I start at B1, so I start when the first element, I go to the nth element. This sounds like a for loop, doesn't it? Right? So maybe I do something like for I is equal to 1 to n, B of I is equal to something, end. Right? Let me just do that. So I would say, I got to define what n is first, I guess. N is going to be the length of x. Oh, no, I'm sorry, that's not true. That's not true. Nm is going to be the size of A. A's got n rows and m columns, so m is going to be the length of x. N is going to be what the length of B is going to be. And I want to go for I is equal to 1 to n. I can come down here and put my n. And bi is going to be equal to something. All right? What is that something? Just take a general B2. B2 is A21, x1, plus A22, x2, plus A23, x3, plus A2m, xm. So bi is really a summation, right? It's you can kind of think of a bi as being going from j is equal to 1 to m, aij, xj. That's one way you can do. That's what this thing is right there, right? You can say that that's ai1 x1 plus ai2 x2 plus ai3 x3 aim xm. That's what that summation would look like. Okay, and we didn't talk about this much, but anytime I see a summation, that's a cue that I've got to do a for loop. All right, this is basically saying for j goes to 1 to m, and this sum is going to be equal to whatever the sum was plus aij xj. So I could rewrite this as saying okay. So let's do that. Let's just say sum. This is a nested loop. There's just an aij times xj, and then this bi is just going to be equal to this sum I did here, so that's sum, and that's it. That's the whole code. It's a nested for loop. There's a for loop within a for loop. Okay, so make sure you understand this line by line. Okay, and what I would do is I would go in and put it into Matlab and create a function file and type it all out and get it right. But make sure you understand line by line what we did here. And if you don't, then rewind the tape and watch it again. Okay, because this kind of thing is really, really important. And it's not intuitive. Okay, I'm willing to bet that a lot of you that are watching this right now are confused and don't know exactly where it came from. But if you watch it over enough times, I think it'll make sense. Okay, and try to understand what each of these lines mean and why I did it exactly like that in each one of those cases. But here's a function file to do matrix vector multiplication. Okay? And in order to do this, I had to write it out on a piece of paper and pencil. I couldn't have gone to Matlab and code and just started typing up. I find it so ridiculous that I see people with nowhere a pencil near them, nowhere a paper near them, and they're just on a computer just staring at it, trying to figure out, like, the code is just going to come to them. You've got to pull out a pencil and paper and try to figure out what's going on and write a code from that. So let's move on. Let's go to systems of linear equations. Systems of linear equations are really important in really all sciences in engineering, especially for reservoir simulation. Because everything we do is we're going to set up a linear system of equations, and the way I teach it in Reservoir 3, the equations will look like this, but in general, they're more along the form of AX is equal to B, which is what I've shown over there. And so it's kind of an extension of what I just did with my matrix vector multiplication, except the difference is that in the example we just did, I gave you A and X and said, find B. With linear systems of equations, I give you A and B, and I say find X, which is a much harder problem. All right, and of course, a system of equations just means that we have as many equations as unknowns. In this case, the A's I know, the B's I know, but the X's I don't. So it's a coefficient times x1 plus a coefficient times x2 plus a coefficient times x3 is equal to b1, and then etc. And you can write that all the coefficients of A in a matrix A, it's a square matrix, and then B is a vector, and X is a vector as well. And unlike the example I just did, where N and M were different, could be different sizes, in this case A has to be a square matrix in order for it to be a well-defined system. X has got N elements, and B has got N elements. X and B are both column vectors. All right. What we want to do is to find X. So given A and given B, we want to find X, or another way to do it is say X is equal to A inverse times B in such a way that it's fast, it's accurate, and it doesn't use a lot of memory. And to be honest, there are hundreds of different ways of solving a linear system of equations. They all have advantages and disadvantages. We're just going to cover an overview of some of them. I bet you've seen some of those methods before. We don't really need to know the details about all of them, but I will go through some of them, and then I'll especially go through the ones that I feel like are good candidates to write little computer codes on to give us some more experience with Matlab. Choosing the best method for solving a system of equations is both a little bit of art and science. So you need a lot of experience. Sometimes you can look at the kind of equations you have and pick the right method. Other times you just kind of need to do some trial and error type things. The right method depends on what kind of accuracy you need. Does it need to be exact, or is close enough good enough? What kind of properties the matrix has, and we'll talk a little bit about that, and how much memory you need in your computer, because your computer can only hold so much memory. Let me discuss a few different definitions, and these are definitions that will be important in our class. So one of them is a sparse matrix. A sparse matrix is one that has got mostly zeros in the off-diagonal terms. So you can have a system of equations, you can have a million by million system of equations. And so that's a huge matrix, obviously. But in reality, most of those elements will just be zero, and only a small percentage of them will have non-zero elements in it. So we call that a sparse matrix. And many problems in science and engineering are sparse matrices, especially in reservoir simulation. And the reason for that is that it sort of depends on the connectivity. So if you've got a reservoir grid, then it's only non-zero if some blocks are connected to each other. And if the blocks from way over there and way over here are not connected, then that row and that column of the matrix will just be zero. And we'll learn about that when we talk about reservoir simulation. There's something called diagonally dominant. A diagonally dominant matrix is one in which the main diagonal of each row is greater than or equal to the sum of the off diagonals. And I should say the absolute value of the main diagonal is greater than or equal to the absolute value of each of the off diagonal terms in that row. So mathematically you can write that this way. So the absolute value of aii is greater than or equal to the sum of aij for all I. A symmetric matrix is one in which the all aij's are equal to aji. So symmetric matrix is exactly what you would think it would be. It's symmetric about it. So actually, the transpose of A is equal to A, because like the fourth row and fifth column of A is the same as the fifth row, fourth column of A. That's what a symmetric matrix is. And that's for all ij, obviously. A positive definite matrix is an important term for matrices. They have special properties which all eigenvalues in the matrix are positive. So x transpose A times x is greater than 0. Now, look, I know a lot of people watch this video don't know what eigenvalues and eigenvectors are. That sounds a little bit confusing. What I will say is that positive definite matrices are important. There are some methods for solving system of equations that require to be positive definite. A matrix that has all positive diagonals, is symmetric and diagonally dominant, is positive definite, although it's possible it can be positive definite and not be all those things. But for our purposes, we'll just say that. If it's got positive diagonals, it's symmetric, and it's diagonally dominant, then it's a positive definite matrix. For our purposes, that's good enough. The condition number. The condition number is a measure of how well conditioned or how singular a matrix is. So, and it really kind of tells the ease of solving the system of equations for some iterative methods. So a condition number of 1 is a very well-conditioned matrix. In fact, you can't have a number lower than 1. So 1 is the best, and then it goes up as high as infinity. And the larger the condition number is, then the less well-conditioned, it's more poorly conditioned. So a value of infinity would be a singular matrix. And if you've got a number that's close to infinity, 1,000,000 or 10 million or something, then we say that that's ill-conditioned or poorly conditioned, and that might be a difficult system of equations to solve. You calculate the condition number as the norm of A, and I briefly talked about norms in one of the previous videos, but you might want to look up some more detail about it. A norm is a measure of the magnitude of a matrix, and then so the condition number is the norm of A times the norm of the inverse of A. And a banded matrix is where most of the elements are 0, so you kind of got a sparse matrix, except you got bands, like diagonal bands near the diagonal that are got elements in it. So we talked about a tridiagonal matrix in the last video we did. That's an example of a banded matrix. You can have a pentadiagonal matrix. You can have other types of banded matrices, but they're basically sparse matrices where you have bands or diagonals with a lot of non-zero terms in them. You can have some zeros in it still, but there's a lot, but they're not all zeros is the point. You get these bands in them. The bandwidth is the distance, the number of columns in between the band. So let me go over here and show you. So if you had a matrix, you had a main diagonal, and then you had these on the tridiagonal, and then over here, then you had zeros everywhere else, right? All zeros all over the place. The bandwidth would be this column. That's the bandwidth. So maybe this is column number 3. Let's say this is column number 317. The bandwidth would be 314, right? So this is J is equal to 3 column, J is equal to 317 column. Maybe this is like a 500 by 500 matrix. This is the bandwidth, right? Some special matrices continued. A diagonal matrix is one that has zeros everywhere except on the main diagonal. So if I is equal to J, so the row and the column, you've got main diagonal terms, but everywhere else you got zeros. That's a diagonal matrix, so of course, right? We know that. There's a Matlab command that allows you to do that, but using the diag command. The inverse of a matrix has a property that A inverse times A is the identity matrix, and A times A inverse is equal to the identity matrix. The inverse is important for solving systems of equations. The identity matrix, if you don't know, is a diagonal matrix with just ones on the main diagonal. So you just got ones on the main diagonal and zeros everywhere. That's what the identity matrix is. In a way, the matrix inverse is kind of like a reciprocal, right? So 4 times 1/4 is equal to 1, or 7 times 1/7 is equal to 1. Sort of the same idea, but don't get confused, because the inverse is definitely not just the reciprocal of all the elements inside the matrix. That would make life really, really easy. That's not how the inverse works. But it's the same kind of idea in that A inverse times A is the identity matrix, or A times A inverse is equal to identity matrix. It's really important for solving a system of equations because let's say we had AX is equal to B. Well, if we knew the inverse, okay, we usually don't, but if we knew the inverse, we can multiply both sides by A inverse, and then A times A inverse is just the identity matrix, and I times X is just X, and so then X would be A inverse times B. So if we knew A inverse, we could just multiply A inverse times B. Unfortunately, finding the inverse is usually more work than solving the system of equations in the first place, so we don't typically do it, but that's what it is. A symmetric matrix, as we saw on the previous slide, is one that's equal to its transpose. So here's an example of a symmetric matrix, right? So 5, 6, and 3 on the main diagonal. Row 1, column 2 is negative 2, as is row 2, column 1. Same thing with row 1, column 3, and row 3, column 1. And you also got on row 2, column 3, and row 3, column 2. So it's symmetric. A tridiagonal matrix is, well, we already know what that is. We talked about tridiagonal matrices. It's one where you get something on the main diagonal and then things on the off diagonal. So there you go. That's exactly the same thing we saw last time. That's a tridiagonal matrix. We learned about it last time. The off diagonal terms don't have to be the same. In fact, you can see we got A, B, and C, and they don't have to be the same as each other. So the example I got on the left has got 2, 2, 2, 2 on the main diagonal. You could have 2, 3, minus 7, 6 on the main diagonal. That's fine. The point is that you've got elements on the main diagonal, elements to the left of the main diagonal, and elements to the right of the main diagonal. They can all be different numbers. It's just, but that's what a tridiagonal matrix is. We just talked about what positive definite matrices are, and diagonally dominants and all that. So this is the same thing over there. So I'm just repeating it myself. Here are some methods for solving linear systems of equations. There are tons of them. There are hundreds of different methods. Here are some common ones. We're going to talk about the direct elimination methods and the iterative stationary methods, but we're not going to talk about, and let me make sure I got the right video here. Yeah, that's what I thought. Okay, I got the right one. So there's things that are called direct methods, which give you exactly the right answer, but are sometimes slow. There are iterative methods, which we'll learn, which are approximate methods, but can be a little bit faster and require less memory. Then there are some iterative non-stationary methods. They're very advanced methods. Many reservoir simulators use them. They are well beyond the scope of what I want to talk about and what's covered in my undergraduate courses, so we won't talk about those or multi-grid methods. They are important. They're just very, very advanced type methods as far as learning how they work mathematically. The simplest method is Gauss elimination, and I think everybody's probably seen Gauss elimination at some point in their life, in high school or in an undergraduate class. Gauss elimination is a method for solving systems of equations. Here's a little, the way it works is you do it in 2 steps. The first is a forward elimination step. And what it does is it creates an upper triangular matrix. So here's basically how this works. If you've got a matrix, you've got a system of equations, show up here. This is 3x1 plus 2x2 is equal to 2. 2x1 plus 6x2 is equal to minus 8. So the A matrix is 3, 2, 2, 6. It's a square 2 by 2 matrix. The B vector is 2 minus 8. What we'll do sometimes is we'll create what's called an augmented matrix. So we create our A matrix right there, and our B vector is 2 minus 8. And to create our upper triangular matrix, we multiply row 1 by 2/3, and we subtract row 1 from it. And so when we do that, we get an equivalent system of equations, and this is the same thing as that. It's just written in a different form to where I've got a 0 in the lower triangle right there. And then what you do is the next step is called back substitution. So what you do is you solve for x2. So minus 14/3 times x2 is equal to 28/3. You solve x2, then you go up to the row above it, and you solve for x1, and so forth. So that's how you get x2 and x1, and the problem solved. That's Gauss elimination. It's done in 2 steps. Sometimes it's called naive Gauss elimination because there are advanced ways to make it a little bit better, like pivoting. But the basic idea is what I've shown on this slide right here. is that you've got your main matrix. This is your A matrix. This is your B vector. We write it augmented. We put like a dashed line or something in between them. And what you do is you mathematically manipulate the equations to remove A21 and A31, right? So you might multiply A11 times A21 divided by A11 and multiply that whole equation. And that's okay. You can do that because as long as you're multiplying the left-hand side of the equation and the right-hand side of the equation by the same thing, you're not changing the meaning of the equations, right? So you do that, and then you subtract this equation from it. You make that a 0. Then you multiply the first equation by A31 over A11 and subtract. You make that a 0. And then that changes these guys. And I put primes there to show that they're different. So then when you got that, you use this as your pivot point. That's what we call as a pivot point. And we use it to remove A32 prime. So you do that, and you get 0. And now I've got an upper triangular matrix. And this is the forward elimination step. Right? So this was a 3 by 3 matrix. The previous slide we did a 2 by 2. You can do a 4 by 4 or 5 by 5, 100 by 100. Okay, you do it by hand and it starts to get really tedious. Anything above about a 3 by 3 or 4 by 4, computer you can do it really fast. Then you do the back substitution step. So we start with this right here and we just back calculate everything. So we go from here to here and we use this equation, A33 double prime times x3 is equal to b3 double prime. Well, that's easy, right? x3 is just b3 double prime divided by a3 double prime, and you get x3. Then you come up here and you say a22 prime times x2 plus a23 prime times x3, which you just calculate is equal to b2. So then you solve for x2. Then you use x3 and x2 to solve for x1. So that's how Gauss elimination works. I'll do a really quick example for you by hand, just in case you've forgotten. I've got this printed out, so if I go too fast, just pause the tape, rewind it, make sure you keep up. See if this comes in. There we go. So that's your system of equations, right? It's a three equations, 3 unknowns. And we want to solve that. So our A matrix, so our A matrix is what I've got on there left, right there. So it's -3, 2, -1, 6, -6, 7, 3, -4, 4. That was the coefficients of my equations. And then the B vector is -1, -7, -6. And I wrote this augmented matrix. I kind of separated it that way. And we want to do Gauss elimination on that to solve for x1, x2, and x3. So what I want to do is I want to use this. Maybe a pencil. That's all right. I want to use this right here as my pivot point to make this a 0 and to make that a 0. All right. So I'm going to multiply row 1 by 2, or by -6 over 3. So I'm going to multiply it by -6 over 3, or 6 over -3, I guess. So 6 divided by -3, if I do that, that will make that a 6, right? So 6, and I'm going to subtract the row 1 from row 2 and then replace row 2 with it. So when you do that, you should get something that looks like this. So I'm going to subtract row 2. I'm going to subtract row 1 from row 2, and then whatever I get, I'm going to replace row 2 with it. And I'm going to get something that looks like this. So that makes that a 0. So the first row doesn't change, -3, 2, -1, -1. Second row is 0, -2, 5. minus 9, so it changed. Then I'm going to still use this as a pivot, and I'm going to use it to get rid of that term. So I'm going to multiply the first row by negative 1, so that makes it a 3, negative 2, 1, 1, and I'm subtract row 1 from row 3, and then replace row 3 with what's left over, and I get a 0 there, and then that makes that 0. Now what I want to do is I want to move my pivot, and I want to make this my pivot and use it to get rid of that. So I'm going to multiply row 2 by 1 and subtract from row 3. And what you'll get is you'll get this. And now this is an upper triangular matrix, right? This is my upper triangle, and that's exactly what you want. Now, I just want to say that some of you may have done this and gotten a slightly different upper triangular matrix. Maybe you added instead of subtracted or multiplied by a negative of what I did, and then you get a different upper triangle. That doesn't necessarily mean you're wrong. There's actually an infinite number of equivalent answers. I recommend just being very consistent in how you do it, especially if you're writing a computer code to do this. You would want to follow a routine. But this is what I get, and that's correct. Then what you do is you do back substitution. And the back substitution is a lot easier than forward elimination. You get minus 2 times x3 is equal to 2, and what you get is x3 is equal to minus 1. Then the next step is what you say is you go to the second row, and I say, well, minus 2x2 plus 5x3 is equal to minus 9. And you plug that in, and you solve for x2, and you get 2. So x3 is minus 1, x2 is equal to 2. You use those, and you plug it into the first row, and I calculate x1 is equal to 2. And if you don't know if that's right or not, what you do is you just take your x1, x2, and x3, put them back into your original system of equations, and see if you get the right answer, right? So to see if you plug those in, if you get negative 1, minus 7, and minus 6. If you do, then it's right. If you don't, you did something wrong. You made an error somewhere. But this is, so you didn't follow that, rewind it and watch it again, but that's how you do Gauss elimination. And there are some advantages. There's no what's called truncation error. Okay, it gives an exact answer. Assuming that you don't lose any digits or anything. But if you use fractions, and you'll get an exact answer. There's a set number of steps. It's very repeated. You know exactly how many steps to use. Some advantages: it takes up a lot of memory. Some disadvantages: the speed is very slow. So the forward elimination step. Okay, remember there are two steps, forward elimination and back substitution. The forward elimination step is relatively slow. It's what was called order n cubed, where n is the size of the matrix, right? The number of equations. So if there's 3 equations and 3 unknowns, n is equal to 3. If there were 100 equations and 100 unknowns, then n is equal to 100. That step is what's said to be order n cubed. What that means, n cubed, means that if I double the number of equations, then 2 to the 3 is 8. So it's 8 times as slow. It takes 8 times as long to solve it. If I did 10 times as many equations, 10 cubed is 1,000. So it takes 1,000 times as long. So if it only took 1 second to solve on a computer to solve 10 equations, then that's not that bad. But let's say I go to 100 equations. That's 10 times many equations. It would take 1,000 seconds. Then it's pretty slow. Okay, the back substitution step isn't quite as bad. It's order n squared. So if you double the number of equations, it's only 4 times as long. Accuracy, there is no truncation error, but in a computer, it does all these additions and subtractions, so you get some round-off error, and that round-off error can accumulate. So sometimes people use what's called pivoting, which is kind of switching the rows and switching the columns in order to minimize that round-off error. There is a slightly better method called LU decomposition. And LU decomposition is another direct method. It's similar to Gauss elimination. What it does is it does the forward elimination step only once. And so let's say you had to solve a system of equations ax is equal to b. But then afterwards, you had to solve another system of equations ax is equal to c. And then you had to do ax is equal to d, and ax is equal to e, and ax is equal to f. And that right-hand side vector kept on changing, but your A matrix, it was always staying the same. Okay? And that's pretty common in reservoir simulation problems where maybe your A matrix, what I've got over here, so in this case this is A, my P is my X, and my right-hand side vector is your little B vector. Maybe this never changes, but this does a lot. Okay? And so with LU decomposition, one of the advantages of it is that you create your upper triangular matrix, you decompose it into an upper triangular and lower triangular matrix, but you only do it once. So the forward elimination step, which is slow, you only have to do it one time. And then in the future, when you do AX is equal to C, and AX is equal to D, and AX is equal to E, you don't have to do that step. You only do the back substitution steps. I don't want to go through all the detail. I feel like that's more appropriate in a different class. But I did want to kind of give you an overview of how LU decomposition works. Basically, if you've got a system of equations like AX is equal to B, or another way to write it is AX minus B is equal to 0. If I were to do forward elimination, you would get UX is equal to D, right? So your A changes into U, your B changes into something different. You call it B prime, call it D, it doesn't matter. So I can write this as UX minus D. And then let's say that there's a lower triangular matrix that if I were to multiply this times L, I would get A. So L times UX minus D is equal to L times U is A, and L times D is equal to B. So if you multiply it out, A is equal to L times U, clearly. L times U times X, A times X, so L times U is A, and L times D is equal to B. Basically, the structure of how that works is you decompose A into an upper triangular matrix and a lower triangular matrix. And then you do that, and then what you do is you solve LD is equal to B, which is just a substitution step. It's actually a forward substitution as opposed to a backward substitution, but they work basically the same way. And then when you get that, you take that D and you use U and you say UX is equal to D, which is also an easy step, and that's a back substitution. So the decomposition step is slow, but once you decompose it U and L, it's really easy. These are substitution steps, which we know are relatively simple. So just to show you one way to do that is if my matrix A was given right here, and I decompose it into L and U, this is a lower triangular matrix. You can see you've got a lower triangle because you get zeros there. This is an upper triangular matrix because I got zeros there. And if you don't believe me, multiply this L times U and you'll see it's equal to A. Then what you do is you solve L times D is equal to B. And I think you can imagine that this step is relatively easy because you can just say 1 times D1 is equal to 3 and you get D1. Then you use D1, plug it into there and you get D2. Then you use D1 and D2 and you get D3. Well, that's great. So you got your D. And then I actually think this is a typo right here. That should be x1, x2, and x3. This D goes right there. This was the solution from that. And you solve UX is equal to D, which is easy. And then that's how you do LU decomposition. And with that, I think I'm going to just pause the video and take a break. So let's move on to another technique for solving systems of equations called Thomas's algorithm. Thomas's algorithm is really a special form of Gauss elimination. But it's only good for tridiagonal systems, which are very special matrices, as we learned. And we learned what a tridiagonal matrix is. It's one where we've got elements on the main diagonal. That's my D's right over there. We got things to the right of the main diagonal. We're calling that with the little A's. And then we got some to the left of the main diagonal, which is the little b's. There's kind of a very structured algorithmic way to do Thomas's algorithm. And basically the idea is the first thing they do is they normalize the first row. So they just divide the entire row by D1. So that makes it D11. It makes the second one A1 divided by D1, which they're calling A1 prime. And then the B, capital B1 is called B1 prime. Right, so that's the first step. Then the second step, well, actually, I guess that's not what I wrote it. The first step is to save the terms as vectors. So what they'll do is they'll say D is equal to this vector of main diagonals, A is equal to the right diagonal and b is equal to the left diagonal. Then they do the normalization step. Then step 3 is an elimination step. So it's basically like doing Gauss elimination. So what they do is they multiply, this basically by b2 and subtract. So they remove that b2 and make it a 0. You can see what's happening there. And you continue to move forward. So then you use this d2 prime to remove b3, and then and so forth. And you continue that on, and you normalize each step. So that in the end, you've got a main diagonal of 1s, and then you got a right diagonal of these a primes, but then you don't have anything to the left anymore. So then it's really trivial to solve that problem, because then 1 xn is just b double prime n, then you use that and you go back and you go back and you go. So you do a back substitution step at that point. But the point is the elimination step is really easy because I don't have to do all these rows. I only have to do one row for each one. That's what makes it easier than Gauss elimination. Rather than making all these zeros, they're already zeros, so it makes it simpler. So it's a simpler version of Gauss elimination. The nice thing about Thomas's algorithm is there's kind of a nice step-by-step way of doing Thomas's algorithm, which I've kind of written out right there. So step 1, you define the vectors. Step 2, you calculate A1 and B1. Step 3, you loop through and you calculate your AI and your BI. Step 4, you calculate BN. And step 5, you calculate the solution using back substitution. So what I would recommend, I'm going to do an example by hand. What I would recommend is, if you've got 2 computers, maybe do that, or maybe if you can print out that algorithm or take a picture with your phone or something, you want to follow along with that as I do this. So let's do a little hand example. And the system of equations we want to solve is 2 minus 1, 0, minus 1, 2, minus 1. One, 0, 0. So clearly that's tridiagonal, right? We got a main diagonal vector, we got an off diagonal to the left, an off diagonal to the right, and then zeros everywhere else, right? It's only a 3 by 3. But step 1 is to define my vector. So B is going to be what's on the off diagonal term. So B was a -1 and a -1, and I got to use a placeholder of 0 for what would have been right there. So that's my -1, -1. D will be 2, 2, 2. That's my main diagonal. My little a will be -1, -1, and then I need a placeholder for over here, so I'll make it a 0. And then capital B will be 1, 0, 0. So step 2 is to normalize that first row, and what we do, and if you go back to, again, and hopefully you printed this out, but if you go back to the desktop, what we say, step 2, calculate A1 is equal to A1 divided by D1, and B1 is equal to what B1 was divided by little d1. So I go back, and I can say, comes up, that little a1 is a1 divided by d1, so that's -1 over 2, right? Because a1 was -1, d1 was 2. Big B1 is 1 right there, divided by d1 is 2, so it's 1/2, which was going to be 1 divided by little d1. All right, step 3. What's step 3? Step 3 says that for I is equal to 2, 3 to n minus 1. Sounds like a good MATLAB function or script file, right? For I is equal to 1, 2, 3 to n minus 1, AI is equal to whatever AI was divided by DI I minus bi, a to the I minus 1. And capital bi is bi minus little bi, bi minus 1. Right, so that's just a little formula that we had for that, okay? So it says start at I is equal to 2, the second row, basically. So we start at the second row, and we go not to the last row, but the n minus 1 row. Now, this one is just a 3 by 3 matrix. So if we skip the first row, we skip the third row, we only have the second row to do. But if we had a 10 by 10 matrix, we would do rows 2, 3, 4, 5, 6, 7, 8, 9. Okay, this one we just do row 2, and that's going to be it. So let's do I is equal to 2, and that makes A2 equal to minus 1 divided by D2 was 2 minus negative 1 minus negative 1/2, and I get minus 1 over 1.5, which is minus 2/3. So that's A23. Then capital B2 is equal to bi, so B2 was 0, right? That was B2 up here, or right there, B2 is 0. Minus negative 1 times 1/3 divided by 2 times negative 1. Minus negative 1 minus 2/3, which is equal to 1/3 divided by 4/3, which is equal to 0.25 or 1/4, whatever you want to do it like that, right? Oh, wait, no, I messed that up. That's, sorry, I think I skipped the next step. B2 should be 0 minus negative 1 times 1/2. I got there. 0 times negative 1 times 1/2 times 2 minus negative 1 minus 1/2. 1/3. All right, so we got A2 and B2. So basically, these are replacing what I had before for A2 and B2, right? That's step 3. So I go from I is equal to 2 to n minus 1, so just the second row in this simple case. And I go back to my formula over here, and it says step 4 is to calculate capital Bn. So capital Bn to step 4. Bn is equal to Bn minus a little bn, bn minus 1. So B3, because n is 3, is B3 minus little b3, capital B2, D3 minus B3 over A2. Now keep in mind that these variables have changed from the beginning, so make sure you use the change properties, not the ones that we had at the very beginning. And if you do it properly, it's 0 minus 1, 1/3, because that's what we just found B2 was 1/3 in the previous step. And D3 still 2 minus 1. We found that A2 was changed to minus 2/3, so you get 1/3 over 4/3, which is 1/4. And step 5 is calculate the solution using back substitution. So xn is equal to bn, and then for I is equal to negative I is equal to n minus 1 to 1, xi is given by that formula. So what we do is we say that x3 is equal to b3. We just found that's going to be 1/4, or 0.25, because xn was equal to bn, right? So we found x3. Now we do xi is equal to bi minus ai xi plus 1. Okay, and we go from the second to last value, n minus 1, which is 2, all the way to 2, which is still 2. So remember, we've only got a 3 by 3 matrix, so that kind of oversimplifies it. But x2 is going to be 1/3 minus 2/3 times 1/4, which I get 1/2. Actually, we go all the way to 1, so I do x1 is equal to b1 minus a1 x2. Therefore, x1 is equal to 1/2 minus negative 1/2 times 1/2. And that's a 1/2 right there. That's equal to 3/4. So my final solution says that x1 is equal to 3/4, x2 is equal to 1/2, and x3 is equal to 1/4. I can plug it back into my original system of equations to make sure that that's right, but I think it is. All right, so hopefully you can do that on your own and get the same thing. That's how you can just follow Thomas's algorithm and do that. But remember, it's only good for tridiagonal systems. Now, let's do something in Matlab. Okay. This is a good problem. This is a problem I've given on homeworks and tests before. So what I would like you to do is just follow go print this out, okay? And you can just follow this step by step, this little algorithm, and try to write a function file to do Thomas's algorithm. So given A, and I'm going to say capital B, that's the right-hand side, just because that's the nomenclature Thomas's algorithm use. Calculate x, where x, ax is equal to b, using Thomas's algorithm. So we want to write a function file to do that, right? And it could be any size A, and well, B would have to have the same number of rows, but any n by n size matrix A. So write a function file to do that. Pause it. What I'd like you to do is to try to do it on your own and just follow the steps in the algorithm and try to write a function file. And I'll give you a hint. You're going to have to do some for loops, but I mean it basically gave it away, right? In that, so it told you when you had to use a for loop. So try to do that and see what you can come up with. So pause the tape and come back and we'll do it together. Now that you're back, let's write it. What's the first line? The first line is function. Actually, you know what? I'm going to go through it quickly. I'll just show you what the result is here, and we'll go through it step by step. So the first line is function x, and maybe you just put x, and that's okay. I put some other things in there, but if you just put x, then that's okay. Is equal to Thomas's algorithm, and your inputs were a and b. All right. So if you got that part right, it's a good start. Okay. Now the first thing we might want to know is how big the matrix is. So A is an n by n matrix and B is an n by 1 vector. So what I could do is I could say n is equal to the length of B. Or you could say nm is equal to the size of A, and n should be equal to m. But either way, you can use the size command or the length command. But that tells us how big the matrix A is. Is it a 3 by 3 or is it a 300 by 300? All right. And then we just follow the steps on there. So step 1 was to define the vectors. So we had a vector A, B, D, and X is our solution. That's what we're looking for. I just made them as zeros. But what I did is I did a little loop to do that. Okay? So it was kind of like what we did with the tridiagonal matrix, right? So it was the same kind of algorithm for that. So I said for I is equal to 1 to n, d of I is the main diagonal, so that's a of I. And then I said b of I is the things to the left of the main diagonal, so that's a of I comma I minus 1. And then a of I is what's to the right of the main diagonal, so that's a of I plus 1. So that's row I, column I plus 1. That's how I did it like that. Now, I just had to put those if statements in there. I did those if statements because, well, if I was on the first row, so if I only did this if I is not equal to 1. So if I was on the first row, then I didn't want to do that. So you could have, another way you could have said if I is greater than 1, that's fine. In the same way over here, if I'm on the last row, then there is no, so my matrix looks something like this. Right, if I'm on my last row right here, then there is nothing to the right. So that's why I got to put my if statement there, just like we did with the tridiagonal in the last video. So that figures out what my main diagonals are, which are D. These are all D's. To the left is what we were calling B, and then the right was what we're calling A, I guess, right? Step 2, we just follow the algorithm step by step. A of 1 is equal to A of 1 divided by D of 1. And ignore all this. And capital B of 1 is equal to B of 1 divided by D of 1. So if you're struggling with this, what I would recommend is to watch the video, this part of the video, a couple times, and then what I would do is I would take this exact code and try to type it up on Matlab and make sure you understand line by line what it's doing and why it's doing that. Step 3, for I is equal to 2 colon to n minus 1. And we just follow the steps. A of I divided by D of I minus B of I times A of I minus 1. So, I was using subscripts in the pseudocode in the PowerPoint presentation, but of course in MATLAB we use the parentheses to indicate the row and column and all that kind of stuff. So that was step 3. It gave it away, right? Step 3 says, look, there it is. So it says, step 3, for I is equal to 2 to n minus 1. A of I is equal to B of I. You practically have to copy it word for word. That's all you need to do there. Step 4 was you calculate B of n. So you put in the formula for B of n that it gave you. And then step 5 was x of n is equal to b of n, and for I is equal to n minus 1. We're going backwards. It's like a back substitution step, right? So we start at n minus 1. We decrease by negative 1, and we go all the way to 1, and x of I is equal to that. And that's our whole solution. So this is the whole code. Try to understand all of that. Okay, you should be able to take something. You certainly should be able to take something like this, which is basically right out the steps for you, and transform that into a MATLAB code. It's just a step-by-step way of doing that. So let me go and pull it up. So here we go. Here's the same code that I showed you a minute ago. I'm going to copy and paste, and I'm going to go to, let's say let's do the same problem I did a moment ago by hand. And I made A was 2 minus 1, 0. Minus 1. 0 minus 1, 2. Oh, I did not do that right. wrong there. So that's A. Capital B, we called it 1, 0, 0. Okay, and then what we want to do is we're going to call it. By the way, even though I got 4, you have to put as many inputs as it asks for. For the outputs, I don't have to put all 4 outputs. I could just put the first 1 or the first 2 or whatever, and it just does it in order. So X is going to be the most important one, so we could just do that if I wanted to. And it'll solve that system of equations. By calling it, I get the answer. So 0.75, 0.5, and 0.25, I think that's exactly what we got by hand. And you could try it with different things if you wanted to. So that's calling Thomas's algorithm to do that. Matlab has a built-in way for solving systems of equations, and you'll really want to know this, so pay attention. You want to solve a system of equations, A/B. It's one of the most powerful tools Matlab has. I use it almost every day. You want to solve a system of equations, X is equal to A/B, and it solves it. Oh, but we called it capital B. So and it gives you the same thing. Okay. Could have also done A inverse, but this is a very inefficient way to do it. You get the same thing. But X is equal to A/B is really powerful. But we get the same thing with our own code, which was Thomas's algorithm, right? X is equal to Thomas's algorithm AB, and it solves it correctly because we wrote a code, which is, we define it, is exactly what we did. So I really think that if you're struggling with the programming a little bit, I think you should type this word for word by yourself, okay, and get this to work, and then go through line by line and try to understand why I did what I did. And it's not the only way to do it. You may have done something different and still gotten it right. Okay, an example was I could have made this if statement a little bit different. Still would have worked. But the basic idea, you should understand how to do that, and you should try to be able to get this yourself, right? That's Thomas's algorithm. The important point about Thomas's algorithm, well, there's 2 important points. The first one is Thomas's algorithm only works for tridiagonal systems. And this will be important in the context of reservoir simulation because one-dimensional reservoirs are tridiagonal, but other dimensional reservoirs are not. So that's important. The other important part about Thomas's algorithm is it's super fast when you can use it. It's order n, unlike Gauss elimination, which we saw was order n cubed, right? So that means with Thomas's algorithm, if you double the number of equations, it's only twice as long to solve it. If you do 10 times as many equations, it's only 10 times as much to solve it, whereas Gauss elimination would have been 1,000 times longer. So Thomas's algorithm is very, very fast. The only problem is it's only good for tridiagonal systems. So there's a summary of the direct methods. Just to summarize some of the things that we talked about. They are exact, but they can be slow when you get to a big system of equations, like 1,000 or 10,000 equations. And it's very common to have a large system of equations. And in reservoir simulators, we can have 1,000,000 equations and 1,000,000 unknowns. Or Saudi Aramco is doing things with 1,000,000,000 equations and 1,000,000,000 unknowns. So that's not uncommon at all. So let me pause the video one more time. Okay, so a different type of technique for solving systems of equations are iterative methods. And the basic idea is you start with a guess value for your solution. So you start with a solution vector x is equal to whatever. You could even guess x is equal to all zeros. You don't know. If you've got a good guess, then use the good guess. But otherwise, you can just guess with all zeros or something like that. And then what you do is you iteratively update the solution. That's kind of the idea. Some of the advantages are well, I shouldn't say there's no round-off error, but the round-off error doesn't propagate and there's not as much. It can potentially be faster than direct methods, and there's a little less memory required, particularly for sparse systems of equations. Some of the disadvantages are they often require the system to be diagonally dominant or positive definite. You do need to tell it when to stop. There's no exact answer. It's an approximate answer, and you have to tell it how much error you're comfortable with. And it can be faster than direct methods, but these stationary iterative methods can still be slow for large systems of equations. Then we go to the non-stationary iterative methods, which are beyond the scope of this course. So these indirective or iterative methods offer alternative idea. So again, we start out with a guess. If you want to, say x is equal to zeros for the solution. So x1 is equal to 0, x2 is equal to 0, x3 is equal to 0, all the way to xn is equal to 0. And the idea is that you've got your system of equations, which is what I've got here on the left, and then what you do is you rewrite your equation to solve for x1 on your first row, x2 on the second row, x3 the third row. So that's just algebraic manipulation, right? So x1 is equal to b1. So you're explicitly calculating x1, and then you explicitly calculate x2, and then you explicitly calculate x3, and so forth. Well, that works out, that'd be great. The problem is that you don't know what, in the first row, what x2, x3, and x4 are. So how can you calculate x1? Well, that's where your guess comes in. And there are different versions of this. One of them is called Jacobi method. That's the simplest and the most basic. Another is called Gauss-Seidel, which is a little bit advanced version of that. And finally, another is a successive or over-relaxation method, or SOR, which is a kind of a more aggressive, more faster technique, or it can be anyway. Now you have to know, now does it converge, okay? So again, the idea is that you guess your x1, x2, x3, and x4, and then you update it, and then you keep on going until hopefully it converges. So if the matrix is diagonally dominant, we talked about what diagonally dominant means earlier, then it's guaranteed to converge. It's possible that it can still converge if it's not diagonally dominant, but you're guaranteed to converge if it is. And remember, we define diagonally dominance in this way. And the picture over here on the right kind of shows examples. If you have two equations and two unknowns, so x1 and x2, what convergence means is that you start with a guess like right here, and you're getting closer and closer to the solution, which is where they intersect. The one on the right is a case where it diverges. So you start here, and you're getting further away from the solution. And that, if you were not diagonally dominant, that might happen. So you might want to check for that. Sometimes you can rearrange your equations, put them in a different order in such a way that it becomes diagonally dominant. Okay, so how does the Jacobi method work? Well, we guess our initial value. So we guess x1, we guess x2, we guess x3, we guess x4, and so forth, all the way to xn. And then what we do is we arrange it just like I showed before. So what we say is we move everything over, so b1 minus all this mess divided by a11, x2, x3, x4. So we're explicitly solving for x1, x2, x3, and x4. And what we do is we plug in our guess values for x2, x3, and x4, and then we use that to get our x1. Then we calculate x2 by putting in our guess values of x1, x3, and x4, and so forth, and we do that. Now the key thing with the Jacobi is that when we calculate a new value of x1 up here, we don't immediately use it in the next equation. So when we go on to the second one, you see that it uses x1. It doesn't use this value of x1 that I've got right here, the one I just calculated. It used my initial guess. And then I go through the whole set of equations. Then when I stop, I go back to the beginning, and I use my new value of x1, x2, x3, and x4. Right? That's how Jacobi works. And so that's kind of what I'm saying there. Mathematically, you can write it like this. That might seem a little confusing to you, although it might be useful to us later when we program. But let me do an example that might be more helpful for how the Jacobi method works. Okay, so we've got three equations and three unknowns, as I've shown on the screen there. I can tell you that the actual solution is x1 is equal to 3, x2 is equal to minus 2.5, and x3 is equal to 7. Okay, that's the actual solution to that system of equations. Now let's use the Jacobi iterative method. And what we probably want to do is we want to find out if it's going to converge, or if it's guaranteed to converge. Now, the absolute value of 3 is greater than the absolute value of negative 0.1 plus the negative 0.2. So 3 is greater than 0.1 plus 0.2, so that's good. 7 is greater than 0.1 plus 0.3, so that's good. 10 is greater than 0.3 plus 0.2, so that's good. So this is guaranteed to converge. I don't know if it's going to take 2 iterations or 2,000 iterations, but it'll get there eventually. That's the key point. So we start out with a guess, and I don't know any better, so I'm just going to guess x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0. If I had a better guess, I might use it, but we'll just use it for now. And we're going to iterate. So iteration number 1. So I'm going to rearrange equation 1 so that it says x1 is equal to 7.85 minus 0.1 times x2 plus 0.2 times x3 divided by 3. Okay, so that's just going to be 7.85 minus 0.1 times 0 plus 0.2 times 0 divided by 3, which is 2.6167. Okay. x2 is minus 19.3 minus 0.1 times x1 plus 0.3 times x3 divided by 7. Now, this is a key point. I'm going to use the superscript 0 to say that's like the 0th iteration. So the x1 I use is not going to be this. It's not going to be that. It's going to be this in the Jacobi method. That's different in Gauss-Seidel. The next method we're going to learn is called Gauss-Seidel. In Gauss-Seidel, I would use that, but I don't use it here. Instead, I just say it's minus 19.3 minus 0.1 times 0 plus 0.3 times 0 divided by 7, which is equal to minus 2.7571. And if I want, I can put my superscript 1 to say this is the first iteration. And it's the same deal, right? It's on this one. So it's 71.4 minus 0.3, but at x1, it's still at the 0th iteration. So I don't use that. And I do not use that. I don't use either one of those. I just still use 0 and 0 divided by 10. And if I put that in, I get 71.4 minus 0.3 times 0 plus 0.2 times 0, right? Or did I do, yeah. Which is 7.14. So that's my updated guess. Now you can tell that that's not the right answer, right? Because we knew the right answer. I told you in advance. Now, you wouldn't know this in real life, but you knew in advance was 3 minus 2.5 and 7, and we got 2.61 minus 2.75 and 7.14. Not bad, really, when you think about it, but it's still not, completely right. Iteration number 2, if I want to get closer to the right answer, then what I do is I say x1 to the second, in the second iteration, is the same deal, plus 0.1. But now I'm going to use x2. I'm going to use this value right there for my x2, my new updated value. And I'm going to use my new x3 right over here. And I get 3.0008. All right. And x3 to 2 is going to be 71.1 minus 0.3 times whatever our value of x1 was, which was, again, this was the 2.61. Okay. Now look at the answers. Okay, the correct value of x was 3, and we had 3.008. The correct value for this was minus 2.5, and we're at 2.488. Correct value of this was 7. So after just 2 iterations, we're really, really close to the right answer. One more iteration, we'd probably be almost spot on. Okay. Technically, you could do an infinite number of iterations to get it perfect if you wanted to go out to like 17 decimal places, but we're probably okay with not quite that good of accuracy. So this is good enough, right? So that's how you do the Jacobi method. Now let's do something more interesting. Let's do a Matlab code to do that. And how do we write Matlab codes? We write them on a piece of paper and pencil. We don't go anywhere near the computer yet. So let's do the Jacobi method. And I'm gonna walk you through this a little bit. We want to compute x given the matrix A, the vector B, and guess values for x, right? So think about when you write a computer program, when you write a function file, when you write function, outputs in brackets, name of the function file, and inputs in parentheses, right? So what do you need to put in parentheses? Think about what I would have to give you if I gave you this problem by hand, right? What would you need to know to solve the problem? You would need to know what A was, you need to know what B is, and you need to know what your guess vector is. You need to know those 3 things. So those are your inputs. What am I asking for you? What am I asking you to calculate? I'm asking you to calculate the solution x. So that's what goes into brackets. So pause the video if you need to and write down the first line of your function file. Okay, we'll call this Jacobi.m, right? So what's the first line of your function file? Should look like this, right? Function, output, x. This is what you're calculating. The name of the file is Jacobi.m, so that's Jacobi. And what do you need to solve the problem? You need to know A, you need to know B, and you need a guess vector of values. So they could just be 0, 0, 0, okay, or maybe you send a different guess values. But that's what you need to know to see it solve the problem. And then, once you do that, you could calculate that problem by hand, or we can use a Matlab code to do that. So that's the first line of our code. So, step 2. Okay. The Jacobi algorithm was an iterative process, right? We did a certain number of iterations. We continued to do it over and over again. So that sounded like a loop, right? So when I did it by hand, I did 2 iterations. I probably stopped a little prematurely. Maybe I wanted to get more accurate, so I would have done 3 or 4 or 5 or 7 iterations. And I wanted to continue to do that until I got below some error criterion, or while the error was too big, right? So I need to do some sort of loop, and I think I just gave away what kind of loop I want to do, right? Is it a for loop or a while loop? I think I just told you that I want to do the iterations while the error is too big, so just by saying it in my head, I said the word while. So it's a while loop, okay? And I want to do it while the error is above some tolerance. So what I'm going to do is I'm going to say while the error is greater than tolerance, and then I'm going to do a bunch of stuff in between. I don't know what that is yet. We're going to have to figure that out. Okay, we'll figure that out together. But this is the main loop. While error is greater than tolerance. Okay, now what is tolerance? Well, tolerance is a really small number. EPS is one of those Matlab built-in variables, and it's the machine precision. It's like 1 times 10 to the minus 16 or something, and it's a really small number. We can't go that small. Okay, we can go a little bit bigger. So I just said 50 times EPS. You could have said 100 times EPS. You could have said, oh, forget all that. I'm just going to say tolerance is 1 times 10 to the minus 7 or something. Okay, whatever you want to do. Okay, but it's a really small number. And then error is going to be 2 times, well, the error has to be bigger than the tolerance just to get things kick-started, right? So if I want to continue this loop while error is greater than tolerance, I better define what tolerance is, and error, at least at the beginning, better be bigger than the tolerance. So that's just why I said error is, whatever I define tolerance is, make the error bigger than that, so at least the first time around it'll enter that loop. That's my thinking there. And then this will make more sense in a little bit, but my solution is going to be x. I sent it x guess, so my best estimate of the solution is x guess. So I say x is equal to x guess, and if I didn't do anything else, that would be the answer. But of course, we're going to update that somewhere in my code. So this is the first part of the code. I hope you understand that. This is the main issue there, right? This is a while loop. While my error is too big, I continue to do all these iterations. So when I did the problem by hand, I just arbitrarily stopped at 2 iterations, but what I really should have done is I should have decided beforehand how much error, I called it tolerance, I was comfortable with, and when that error got below the tolerance, then I'd say, okay, I've done enough iterations. I don't know if it was going to be 3 iterations or 7 iterations or 700 iterations, but we'll stop when we get there. That's why it's a while loop. That's why it's not a for loop, because I don't know if it's going to be 3 or 7 or 700 iterations in advance. It's like running around that track, and I tell you just to stop whenever you get to 15 minutes. Same idea here. We're going to stop whenever the error gets below the tolerance, however many iterations that takes. So we've got a while loop. Okay. Now, in that while loop, we know what we did by hand, right? What we did is we calculated x1 using the guess values for x2 and x3 and x4 and x5. Then I calculated x2. Then I calculated x3. Then I calculated x4. And then I went all the way to x to the n, right? So I did something that looked like this. Okay. If I wanted to draw it out mathematically, this is what I did. Okay, if you're a little intimidated by the summations on the right, don't worry about those yet. The point is, what we did is we calculated x1 is equal to that. Okay, we said x1 is equal to b1 minus all that divided by a11. Then we calculated x2 is equal to b2 minus a. Then we calculated x3. Okay, then we calculated xi. Right, so x1, x2, x3, x4, x5. Okay, or I can call it just in general xi. We went all the way to xn. So this is another loop. I do it a set number of times. I do it n number of times. So I start at x is equal to 1, and I go all the way to xn. Okay, and then in between I've got a formula for it. So the main part of my loop is given in here. So, well, I haven't shown it yet. If you want, pause the video and try to do it yourself. Okay, and I think you should be able to do just this part of the code, the for loop part of the code. Okay, the main part is given in bold. So the stuff that's not in bold is already written there from the last step. Well, one thing I might want to know is what n is. N is just the length of, well, this is actually, I got a few typos in here, I think. So this is the length of b or the length of x guess. Or maybe I should have written that over there. Okay, so there are a few typos in here, but the main point is still there. So n is equal to the length of this vector or the length of that vector. You could have done either one. And then what we do is we say for I is equal to n, my x of I, or I called it x new of I. You can call it whatever you want. I wanted to change a different variable just so I don't confuse myself with what x was before. Because remember, we don't want to update x until the end of the loop, right? That's how Jacobi method works. So I called it x new, and I said x new of I is equal to b of I minus this term in parentheses, which I'm going to call sum, divided by a of I. So for I goes to 1 to n, x new of I is equal to b of I minus sum divided by a of I n. So this is a for loop within a while loop. Remember, we're iterating through iterations. So in iteration 1, I calculate all my x news, and then I stop, and then I go to iteration number 2, and I do it again, and then I stop, I do iteration number 3, and so forth. That's how the method works. Okay? So this is really the main part of my code. Now, what is the sum equal to? Let's figure that out. I need to compute a sum, and let's go back and look at it up here. Actually, this might be better. So what we had was x of I is equal to bi minus this term in parentheses, which was ai1 x2 plus, oh, that shouldn't be an x2, that should be an I. Oh, no, it should be, that's right. ai1 x2 plus ai2 x3. Basically, what it is this. It's bi minus the summation from j is equal, I'm going to write it out so it's more clear to you. Remember what our equations were. They were a11 x1 plus a12 x2 plus a13 x3 okay, or in general, what we had was ai1 x1 plus ai2. So this is for the ith row. Bi. So if I wanted to solve for the xi, which one that one was, what you would have is xi is equal to bi minus divided by aii. But one point in here is that this would have skipped the aii xi term because that's what you're solving for. So if I was 3 in this case, then you would do that. So I should say we skip that term. So when you write this xi, it's equal to bi minus, this is a summation, ai, this will be our j, times xj, where j goes from 1 to n, except that j cannot equal to I because of this region right over there, divided by aii, where this is my sum. So my xi was equal to b of I minus my sum divided by aii. Now, I think I mentioned this in the other videos, but anytime I see a summation, then that's a hint to me that that's a for loop. A summation is a perfect example of a for loop. And it's so easy. You just look at it and you say, look, for j goes from 1 to n, okay, this is a sum, so I want to say sum is equal to 0, and then sum is equal to sum plus aij times x of j, and with one little caveat, I say if I does not equal to j, end, right? Because you skip over that term in the sum if I is equal to j. So that's what we do right there. So this is equivalent to this. Where j does not equal to I. Okay, that's the programming version of that summation. So if I go to my code now, that's exactly what I did. So I'm building up my code here. And the stuff in bold is new. Everything else we had written in the previous steps. So in steps 1, 2, and 3. So this is three nested loops with an if statement. This is about as hard as you get. Okay, so if you're understanding this code, you're doing really, really, really well. And if you don't understand it, try to start all over from the beginning, do the problem by hand again, try to understand what I'm doing and get it. Because if you can get this code, you're in pretty good shape. So, because think about it, we got a while loop, a for loop, and an if statement. All right, that's about as complicated as you get. This is the new part. This is the same thing as our sum of j is equal to 1 to n, where I is not equal to j. That's why we've got the if I is not equal to j of my aij, and I probably should have ij times x of j, right? Or I was using subscripts before, but it doesn't. You get the same point from that, right? That's the same thing as that. This for loop is just looping through the rows. This is for my different iterations, and let's move on to another step. Okay, so we're doing that while loop, and we continue to do those iterations. We're calculating our new x's, and we stop. We need to stop when we calculate an error. Once the error gets small enough below the tolerance, we know we're done. That's how the while loop works, right? We continue to do the iterations while the error is too big. So I need to calculate an error in every while loop iteration so that I know when I can stop. The error, you can define an error a bunch of different ways, right? So the error is a difference, in this case, well, the true error would be the difference between the exact answer and what we think the answer is, but we don't know the exact answers. That doesn't do us any good. In our case, we're going to say the error is the current guess of x compared to what it was in the previous iteration. And when that doesn't change very much anymore, then I can say I'm done. So if I got x is equal to 3.1 last time, and then the next time I get 3.1002, then I'm like, well, that's not really changing very much, so it's probably good enough. But of course, there's an error associated with every x. You can have an error for x1, an error for x2, an error for x3, an error for an x4, all the way to xn. So we'll do each one, and then we'll use the biggest one of all of them to figure that out. So I'm going to say the error for xi is, I'm going to call I underscore error, and it's just the old value of x and the new minus the new value of x divided by the old value. So it's like a relative error, right? So this is what's new in bold down here. I define error of I. Notice where I put it. I put it within inside this for loop. Error of I is x new of I minus x of I divided by x of I. So this is my new value. This is my old value divided by old value. So I mentioned it earlier, but the reason why I used the new variable x new is because I didn't want it to wipe out the old value of x, and then I can calculate an error and do some of that. And then outside the for loop, I can calculate the maximum value, and the easiest way to do that is that Matlab's got a built-in variable called max, and so error of I is a whole vector of x's, errors, error for the first x, the second x, the third x, etc. And this error is the maximum of all of them. And then, once I do that, then I can say, well, I calculated a new x. Now let's make that the new value of x, right? So x is equal to x new, and then it starts the whole process again. It calculates a new x, which is different from that, and then I switch it up again, and I keep on going. So you can do this whole code if you want. You can type it in. And I think, let me see what I did. I did some little other things in there. You can make your code even better. So maybe I want to count how many iterations I did, right? So I don't know if it's going to take 2 or 7 or 700 iterations. So I added something where I counted the iterations. It's like a counter. So every time I get inside the while loop, I add 1 to it. So then I could print that out as an output if I wanted, call it iter. I also might want to print out my final error and do that. Another thing that I could do to make my code even better is I could say while error is greater than tolerance and iter is less than 1,000 or something. Because maybe if I get over 1,000 iterations and I'm like, look, I don't have time for all this. We need to get out of the loop and do something else. Or the thing's not converging or something. So you do that. And you could make your code even better. You could even do something at the beginning of the code where it checks to see if it's diagonally dominant or not. So then you know if it's going to converge. You can do other neat things. But this is just kind of the base that does this. But again, this is not an easy code to write. Okay, so if the first time you watch this, you struggled a little bit, but don't worry about it. It's a tough code. It's got a while loop. It's got 2 for loops. It's got an if statement. It's got some other stuff in it. Just pause the video, watch it again, type it up yourself in Matlab and see if you get it to work. I could show you my code, which should be identical or almost identical to what I had written over there. I think that file, open, Jacobi. So I think that this is exactly the same, or it's close to being exactly the same as what I had shown by hand. So it's awfully close. Let me go to, hopefully you can see this. I'm going to change the font. Still a little. I did some things over here that I didn't necessarily need to do. I don't think I needed all that, but I did some things slightly different. I don't know if they're necessary, but basically it's exactly what we had written down on my little Word doc. And here you go. So here's an example where I did add I said max iterations is 1,000, and do while the error is greater than tolerance and iterations greater than max it. And what we can do is we can call my Jacobi to see if it works. Oh, I shouldn't have cleared all my... Let's do the same... Well, let's do the one that I just did, where I had my A matrix was 3 minus 0.1 minus 0.2, 0.1, 7 minus 0.3, 0.3 minus 0.2, 10. So I think this is the same matrix we had in my hand example. I said B is equal to 7.8 5 okay, and so the correct answer is 3 minus 0.257, and I use that backslash operator because I know that's MATLAB's really fast and fancy way of doing systems of equations. But let's say I want to use my method. I'm going to do A, B. I'm going to send my guess values. I'll just send it 0, 0, 0. See if that works. And it's going to calculate the solution, the number of iterations, and the error. So the solution, oh, it worked. Look at that. It got x is equal to 3 minus 2.5 and 7. It took 13 iterations. Okay, remember when we did by hand, we only did 2, but the error it got down to was ridiculously small. It was like 10 to the minus 16, and you could tell because it looks like the exact answer. It's 3 minus 2.5 and 7. Let me do, if I did format long, I wonder if we get any error. Probably not. Okay, a little bit. You get a little 2 there at the back of the 7. But for all practical purposes, it gets the exact answer because I did enough iterations to do that. It's technically not exact. There's still a little bit of error, but you wouldn't notice it. So, yeah. So if this is a good problem to practice on. And if you don't get it, then keep on doing it and try to type it up and try to get it to work. And if you can understand how to do this one, I think you're in really good shape. So the example problems like this one and the Thomas's algorithm and the tridiagonal matrix and the matrix vector multiplication, the ones that we've been doing, if you can really understand those, then that kind of covers most of the important stuff. Let's finish up with, so I did a little Jacobi example here, 2 by 2. You can do this one. We already did a 3 by 3, so I'm not going to do that. Gauss-Seidel is like Jacobi. The difference is that unlike Jacobi, when I calculate a new value of like for x1, I don't wait till the end of the iteration to use it. I use it as soon as I can. It's like being really aggressive. What it does, as soon as I get a new x1, I use it as fast as I can. And so kind of a pictorial way of doing that is over here. So you see I calculate x1, and then I immediately use it in there. And then when I get to x3, I use that x1 and that x2, and I plug those into there. And the second iteration, I use them as immediately too. So I use everything as soon as it becomes available. And the reason I do that is I'm thinking that, well, when I calculate x1, that's a better guess value of x1, so I'm use it as soon as possible. And so I'm not going to go through the details of that. So here's sort of an example where I've got this 2 by 2 system. I solve for x1, then I take x1 and I immediately put it into x2. Then I do x2 and I use that and so forth, and eventually it converges to the solution. And you can compare that to the Jacobi example. You could also do the hand example I did with Jacobi earlier, but do it with Gauss-Seidel and see what happens. So there's one last method which is similar to Jacobi and Gauss-Seidel. It's actually an extension of Gauss-Seidel. So it's really Gauss-Seidel with relaxation. And what it does is it weights the old value and the new guesses to get an updated value. So what it does is, don't worry too much about the second term. What it does is that when you calculate xi, the new value, the new iteration, it multiplies it by a weighting factor, and then it multiplies the old guess by a weighting factor. And if you use omega is equal to 1, it's just Gauss-Seidel, right? You just use whatever you got for that. Under relaxation is when you choose an omega value that's between 0 and 1. So if you choose like 0.5 or 0.9, it's really not over relaxation, it's under relaxation. And in that case, you're putting more weight on the old value. If you use over relaxation, you're using a value between 1 and 2, and you're putting more weight on the new value. So what you're kind of doing is saying, look, I got a new value of x. I think I'm moving in the right direction. Why don't I just be overly aggressive and just put even more weight on that? And so that's how you do that. Choosing the value of omega is not so simple. It's usually more trial and error, and there are some techniques to do that. But anyway, you can do some examples of that if you want. You could choose an omega of like 1.2. You can choose an omega of 0.8 and do that same problem we did with Jacobi, but use it with Gauss-Seidel with relaxation. If you use an omega greater than 1, then it might converge faster, but it might not converge at all. So you got to be careful with it. That's the downside of using a value of omega that's too big. Using a value of omega of less than 1 will converge slower, but it's more likely to converge. It does it in a more steady fashion. You never want to use omega values that are less than 0 or greater than 2. They'll diverge, so don't do that. It's got to be between 0 and 2, but omega 1 is the same thing as Gauss-Seidel. With that, I think it completes the 5th part of this review series on linear systems of equations. We may a couple more advanced topic videos, but for now, this kind of concludes the main points of programming in Matlab and linear systems of equations. Thanks.